Hello, everyone. I'm Christy Risk, Senior Editor at GenomeWeb, and I'll be your moderator for today. The title of today's webinar is Accelerating Patient Diagnosis with Automated Literature Curation for Inherited Disease, and our sponsor is Genomics. Our panelists today are Dr. Birgit Funke, Vice President of Clinical Affairs at Veritas Genetics, and Dr. Mark Kiel, Founder and Chief Scientific Officer of Genomics. You may type in a question at any time during the webinar. You can do this through the control panel, which usually appears on the right side of your screen. Click on the Q&A box on the upper right side of the control panel. When you click on Send To, please select All Panelists. We will ask the panelists questions after the presentations have concluded. Dr. Funke, please go ahead.
Thank you very much. I'm very excited to share my thoughts on one of my favorite topics with all of you today. So let me jump right in. Why are we here? Why is this one of my favorite topics? Also, from my perspective, NGS, next generation sequencing, has dramatically changed molecular medicine. We have large gene panels these days, and they're more and more established. We're rapidly moving to universal whole exome and whole genome sequencing, as I'm sure you all know. And I will say the utility of comprehensive medical sequencing is increasingly recognized. Today, there's a strong incentive to implement this into clinical care, and a growing number of labs adopt NGS. And as I said above, the trend towards clinical exome genome sequencing is increasing. So in a nutshell, I think we are on the verge of harnessing the power of genomic medicine that's been promised to us for so long. The goals are simple, deceivingly simple. We want to explain the patient's genetic disease. We come out of the diagnostic era. We do want to use that knowledge once we have established causality to predict disease in those who have not yet developed it. And we want to do all of that, of course, quickly and inexpensively and accurately. So just a little bit more background. Genetic disease was initially believed to be quite rare, so initially meaning 30, 40, 50 years ago, but that's not at all the case. We know better today, and I want to show you a couple of facts about my favorite genetic disease area, inherited cardiomyopathies, which happens to be one of the most common genetic disorders. And so what you see here on this slide are a couple of key facts. You see the main cardiomyopathies represented, but that's not the topic of the talk. The points I want to make is that they're collectively very common. So more than 1 in 500 individuals have a pathogenic variant, and they can all lead to sudden death. So that means there's a huge incentive for predictive testing. And, I would say most hospitals and laboratories have some form of cardiomyopathy testing in place. And in fact, the ACMG, the American College for Medical Genetics and Genomics, is recommending the return of positive findings regardless of the test indication for a lot of these cardiomyopathy genes. They're part of the famous ACMG 59. So in terms of history, it's kind of nice to look back and see where we came from and what caused actually the issues that we're grappling with today. Shown here is an overview of a timeline for cardiomyopathy, and this is adapted from a nice paper by Barry Maron. The first gene really catalyzed this whole evolution, the first gene discovery, I should say, and that was made in 1990, so almost 30 years ago, the MYH7 gene. A few years later, the second gene was discovered, and then about 15 years ago, real commercial testing started. And if you now want to switch to the timeline below, that depicts now what happened at one laboratory, which happened to be the lab that I was at the time for about a decade, the Laboratory for Molecular Medicine. We began offering these tests in 2003, and they were tiny compared to today's standards, just a handful of genes. We went through an evolution of adding, panels for each cardiomyopathy type, HCM, DCM, ARVC, and that was done in other disease areas as well. And then in 2011, we transitioned into next generation sequencing. And with that, I would say our problems on not being able to manage information really began. So now we had one large panel, 46 genes, and the next slides will take you through some of the issues. So again, to reiterate the goal, how can we make genomics available to all? And by all, I now mean those who are sick and need a diagnosis. But increasingly, this type of work is used for predictive purposes, and we want to just really make it available to everybody. We know that sequencing costs have dramatically decreased. That is decreasingly an issue. Automation is helping, and we know, as I said, genetic data is thought to be increasingly useful. But there's strong opposing forces that really have been barriers, such as you all know, minimal to no reimbursement for this type of testing. Not even for diagnostics, you know, nobody reimburses for prevention these days. So one of the only solutions, besides convincing payers that that should be reimbursed, is to aggressively work on lowering the interpretive costs. And why am I saying this? What we didn't see coming in the beginning, and I've been with this area for the last 15 years and have seen it grow, I can attest to the fact that we didn't think about this avalanche. We were unaware what was coming toward us, and the avalanche means the avalanche of variants that we now need to interpret. The graph to the right is from a nice paper that came out of the Laboratory for Molecular Medicine, and what it shows you is the percentage of novel variants broken down by variant type. So to orient you, the diamonds are the benign spectrum variants. The squares show you the likely path and pathogenic variants, and then the triangles show the increasing test volume from 2004 to 2013. And the hope back then, when we started testing, so in the early 2000s, was, well, pretty soon we will have interpreted all variants, and then genetic testing is going to be inexpensive and fast because we can just go back to what we already interpreted. And little did we know, it came true for the likely benign and benign variants, but also not as quickly as we thought. You see that that graph goes down to a very manageable percentage in like 2009, 2010, and has stayed down there. But look at the likely pathogenic and pathogenic variants. After 10 years of testing, still 40% of clinically significant variants remained novel. So that is something that we and others completely underestimated. And here's another way to look at the same phenomenon. Many of these variants are unique, and that's why we continue to see so many novel ones. This is shown here again for hypertrophic cardiomyopathy. This shows data from about 3,000 probands from the LMM, and what you see here is that 2/3, 63%, have been seen only once. And then to the right of this graph, you see a few rare variants that can be called common. Not even that common. So the most common one has been seen 45 times in our laboratory. So the interpretation needs are not going away. In fact, we have created ourselves a humongous bottleneck by expanding our tests to more and more genes, which means that we have to put in more and more time to make sense of what we're finding. And again, the $1,000 genome is a reality today. That is in place, so we can stop worrying about the reagent costs, but the interpretation has been, playfully, described as this $1 million interpretation. It's certainly not quite as much, but it, is certainly enough, and is the bottleneck that we have to battle. What are these barriers to scaling variant interpretation? Well, number one is just the sheer number of variants we have to look at, especially when you have these large panels. My favorite in there, the biggest enemy is unstructured data, and we'll get into that a little bit. It means that we need highly trained individuals to extract and assemble critical evidence. And human labor, as we all know, is expensive, especially when you add on MD and PhD degrees that are required to really understand the data. We do have interpretation guidelines, but they're also kind of still in their infancy. They have some weaknesses. We're rapidly improving them, but they're not bulletproof. And, safe to say that fully integrated pipelines just are very rare to non-existent. So in addition, I would like to mention that we as a community, a clinical testing community, have been given the mandate to reinterpret, meaning that we're being asked by professional societies to keep an eye on newly emerging knowledge and make an effort to continuously reinterpret what we have already interpreted, and that just is completely infeasible at this point. I mean, most of us are still struggling to stay afloat with our daily operations. So we need to figure out a new approach, and this is what the rest of the presentation is dedicated to. Most of you will be aware of the ACMG-AMP variant interpretation guidelines. So sorry for the omission of the AMP in the title of the slide, but it's on the title of the paper. This has been a landmark change. It was published only a few years ago in 2015 and is now on its way to becoming a worldwide standard. As you can see in the little box below, the UK adopted it in 2016. It's been published in Chinese in 2017, and it's now used by 95% of the labs worldwide, according to some surveys. So what are our problems? There are two that I want to go through, and the first one is finding the right publication. I would say it's not trivial. Hang on. Just to remind you, why am I even talking about finding publications? There are two types of data elements that the ACMG-AMP framework wants us to consider. One type is easy to extract. So, those are population data, computational data. Nobody struggles tremendously with that. When it gets to essential evidence such as functional studies, case studies, segregation data, et cetera, those are the types of data that are still just in the primary literature. There is no centralized database that has it nicely structured to retrieve. We're all working on this as a community. There are consortia that are operating in this space, but this will take years. So until then, we are left with the need to painstakingly read publications and extract those data ourselves. So there are two types of problems that one can encounter and should be aware of. One, so I put a fictitious variant up here and did a Google Scholar search, which is a very commonly used tool in addition to others. But this slide here shows one of the problems. Well, the question is, am I missing any publications? This variant search did not return anything, but did I do the right search? Is there really nothing out there, or did I just not put in the right keywords? That's one problem. The inverse is also true. So this one shows you actually the most common variant for hypertrophic cardiomyopathy. And you see that there are 853 search results. So if you didn't know anything about this gene, this variant, you may be slightly overwhelmed, and you know that all of these are not necessary to be read, but which ones should you pick? So that is your specificity problem. The second problem is extracting the right information. Now, once you've found your papers, extracting the right information is equally difficult. And those of you who are operating in the germline space will certainly have come across this particular problem here. A lot of genetic information that we're being asked by our framework to extract is very complex. So you're looking at a pedigree or pedigrees from a certain publication, and there's a staggering number of different ways out there that authors show their pedigrees, format their pedigrees with, and there's absolutely no standardization. And you have to really look at this and understand, on top of understanding the genetic, the science behind it, you have to also understand how the authors labeled something, and there's just no consistency between papers, even within papers. And if you're unlucky, there's just text. The right part of the slide shows you a text-based description of a family in which a variant segregates. So now on top of having to understand this text, you have to construct your pedigree yourself. So that can take time and a lot of knowledge. We became aware of the Mastermind tool a few years back, and were immediately intrigued. This company has indexed the genomic literature, that I'm translating this to searched or pre-read the genomic literature with key terms for diseases, genes, and variants for a humongous number of variants, and Mark Kiel will tell you more about the tool later. And we thought this would be worth exploring, whether or not it can help us slim down the time that it takes to fish out the right publications. So the next few slides are talking about that exact topic, and this was a pilot project conducted by a fellow at the time at the Laboratory for Molecular Medicine, Ryan Schmidt. He's now moved on to Children's Hospital in Los Angeles and is assistant professor there. So thank you for his, I want to thank him for his slides. The concept was simple. So we used my favorite disease area, cardiomyopathy, and asked the following question: can we, if we searched using this tool for the following genes, and they're kind of small, they're on the upper left-hand side, following 10 genes, are we able to find the right papers? Is it as good as conventional search strategies, including PubMed, a subtype of PubMed called PubMed Mesh, and then Mastermind was the third one that we compared PubMed and PubMed Mesh to. And what Ryan did is he conducted a search 3 times and then analyzed the papers, the abstract that came out for relevance, and then asked the question, how good are these 3 approaches relative to each other? Now, Mastermind, it's fair to say, resulted in a humongous improvement in sensitivity. What you see here are is a Venn diagram showing the number of papers found. And you can see that across all genes, Mastermind found a really enormous number of papers that have been missed by PubMed or PubMed Mesh. Initially, it missed a few. There were a lot of improvements made, and so we would, today think that it misses a very, very, very small number. Not 0, but we also asked the next question: does it find the right stuff? So yes, it finds a lot of papers, but are the good ones that we want to see among them? So Ryan plotted it this way, and now what you see here is a color-coded way of showing the information. In black, he went through every paper and then sorted them by relevance. In black are the ones that were deemed highly relevant, and in color are the ones that aren't. And you can see the left one is Mastermind, and the next one is PubMed sorted by best match, and then there's another PubMed sorting algorithm. And essentially, Mastermind and PubMed using this approach look very similar, so the relevant papers do come to the top. And let me see. So we concluded at this point that Mastermind was very useful to enhance these disease gene curations. And so we piloted that in the context for disease gene validity assertions. Of course, it's the same thing for variant disease assertions, so there's no difference there. And we believe that it's extremely useful. That said, the specificity problem remains. I told you it finds a lot of papers, and I believe Mark Kiel will now tell you a little bit more about how that problem is continuously improved. And so with that, I'm at the end. I'm going to turn it over to Mark.
Thank you, Dr. Funk. As a reminder to webinar participants, if you have a question, please type it into the Q&A box in the control panel. We will conduct the Q&A portion of the webinar after the presentations have concluded. Next up is Dr. Kiel. Please go ahead.
Thank you, Christy, and thank you all attendees for participating with us in this webinar. Thank you, Birgit, for setting up my portion of the talk. I'm going to emphasize here that what I'm going to talk about is the improvements and enhancements in the specificity of the Mastermind search engine, and particularly highlight the fact that we've now gone at the variant level in this work that we've conducted with Veritas over some 15, 18 months. And also to emphasize, as Birgit suggested, that this is a work in constant evolution, and so we're excellent at this point, but we're hoping to be even better at improving our sensitivity specificity distributions. So specifically what I'm going to be talking about is accelerating patient diagnosis using the Mastermind platform, which provides automated literature curation for inherited diseases in this context, but also for somatic disease and cancer. So what is Mastermind? Mastermind is a genomic search engine. The database that we've collected by indexing these many millions of full-text scientific articles comprises every disease in the whole spectrum of human disease, no matter how they may be described in the paper or searched by our users, every gene in the entire human genome using the conventional HGNC gene symbols or any other synonym or alias or previous name for those genes. And then once we've identified that a gene is mentioned in any one of these papers, in any part of the full text, we index the rest of that article, as we do for every article, for the mention of any one of billions of possible genetic variants in any of the genes mentioned in that reference, no matter how it may be described, whether it's described at the cDNA level, at the protein level, or described as an RSID, and whether or not the cDNA and protein level descriptions conform to the standard HGVS variant nomenclature. We also layer on top of that indexing process many hundreds of clinically relevant key terms, which I'll highlight here in a moment, that's particularly germane to the ACMG AMP classification schema. And then all of that data is organized so that a user can search by disease to see all the genes and all the variants in those genes that have been associated with that disease, or otherwise, and in the case that I'm going to highlight here in a moment, search by a particular variant and know what papers have mentioned that variant, how many times each of those papers have described that variant, what diseases are also co-mentioned and highlighted in those references, and then which of those papers is most likely to be relevant to the curation at hand. And that's what I want to spend most of my portion of this talk describing. A couple of slides here that take you a bit deeper into the Mastermind software. It's cloud-based, it's on the web, it's freely accessible, and there is a professional version, but all of the data in both the free version and the professional version is basically the same. The same variant information, the same disease information is provided to free users as to professional users. This is a reflection of some of the data visualizations that Mastermind offers the users. On the left is a visual depiction of the literature landscape that satisfies user-defined filter criteria, which could include a particular variant, may also include a specific disease, and could also additionally include any one of those relevant clinical key terms that I described. What you're seeing on the left there in that depiction is individual articles represented by circular icons, the size of which is an indication of the relevance of that content to your specific query. And the relevance of the content is defined by the number of times that a certain key term is mentioned, where in the hierarchy of the paper that term is mentioned, in the title, the abstract, or somewhere in the full text, and then how close together the terms are mentioned. For instance, a clinically relevant key term may be mentioned adjacent to or in the same sentence with a relevant variant that has been searched for. That would augment the relevance that Mastermind calculates and presents in this plot. And then to further enhance the utility of this visualization, along the x-axis is the publication date of the reference, and on the y-axis is the impact factor for that particular journal. So at the upper left would be high impact seminal papers that describe the initial mentions of a gene or a variant or a disease gene variant combination, whereas over toward the right of this axis would be more recently published references. So it depends on what your clinical question is as to which area of that plot you focus on. But then I think critical to the success and the high degree of utility of the Mastermind interface is we don't expect our users to take our word for our various assertions and prioritizations, we show the evidence that indicates that, in fact, this reference is talking about the variant that was searched for and is, in fact, pertinent to the user's clinical search. And a couple of ways to exemplify that. One is that we show that match frequency that I was describing. So we've found in the work that we've done with Veritas, that I'll describe here in a moment, one of the many important criteria, probably the most important, is the frequency of the mention of a particular key term. Particularly relevant when you're doing variant interpretation would be the frequency of the mention of that variant in the paper. And so we display that frequency on the right, in the upper right quadrant of that image. That's where we depict the frequency of mentions of a variant. And then below that, we actually demonstrate what sentences from the full text actually discuss that variant, or otherwise describe clinically relevant key terms, or otherwise talk about the gene of interest. And so again, the intent of using Mastermind there is to streamline the identification of relevant content and the process of convincing yourself as a variant curator that this is in fact the most relevant content, the most specific information that can be used for your ACMG AMP classification. So again, talking a little bit more about our enhancements to the specificity of the results that we returned. Birgit did a great job talking about the sensitivity aspect, where the idea that Mastermind is not missing a significant number, sometimes any of the references that are available. What we're now talking about doing in one of the examples that she highlighted is enhancing the top most prioritized search results, which is highly useful in the circumstance where hundreds of papers are returned, and a variant scientist is, say, not as familiar with the variant or the disease and would like to get to those most relevant articles most quickly. So this is one of the strategies that we've invoked. It gets back to those clinically relevant key terms that I described, which is part of our indexing process for every one of these millions of full-text references. In this case, what you can see are about a dozen subcategories of the ACMG AMP classification guidelines. They're bucketed together here because clinically focused questions typically address one of those subcategories, but they can be combined using multi-parameter group or individual keyword searches. The one that I'm highlighting in particular is one of the many ACMG AMP subclassifications that requires getting information from the medical literature, which is what Mastermind specializes in, and that's the PS3, BS3 designation, so strong evidence for pathogenicity or strong evidence that this variant is benign based on functionally relevant studies. And so taking you a step further, these are some of those clinically relevant key terms in this subcategory of functional studies. We've even subdivided it further into studies that suggest that there's in vivo evidence of pathogenicity. There's a subcategory here for functional for in vitro, and we've dichotomized those because some of the labs prefer not to use in vitro studies, whereas other labs include either in vivo or in vitro. But what you're seeing here is a list of some of those keywords, and every one of those subcategories has their own custom list. The number there is a reflection of, for the number of articles that Mastermind has identified contain your variant of interest, how many of those articles also touch upon, say, knock-in mouse models of functional significance. And so again, those individual keywords can be selected, or so too can subgroups or entire groups or multiple groups of the ACMG classification schema. And so that's useful for filtering out articles that are not relevant because they don't contain any of those keywords. It's also useful for prioritizing the references, in some situations many hundreds of references, and then also, as I mentioned earlier, displaying the evidence so that there's a very quick process of identifying and confirming the most relevant content for your particular variant search in the Mastermind database. So let's get to the work that we did, Birgit and I supervised from Veritas and Genominon's collaboration. Again, it's along the lines of enhancing the specificity of the Mastermind search results with particular emphasis on variant-level reference identification for ACMG AMP classification. So the way this study was architected between Veritas and Genominon was that we took 36 variants that were identified from routine variant interpretation operations over the course of the past couple of years at Veritas, and we identified references that were used in Veritas's clinical classification, which at that point was identified using a combination of PubMed and Google Scholar searches, which Birgit highlighted a bit earlier. And then separately, we compared those results to the results that were garnered from searches for those same variants using Mastermind. All of those references collectively, and for the 36 variants in total, it was 3,600 articles, they were manually reviewed in a blinded way. So we collected all those references, and then we forgot or had our curators ignore where the references came from. We curated them for relevance, and then we revealed what the source of those articles were, whether it was Veritas alone, Veritas and Mastermind, or just Mastermind alone, and we compared the specificity of the search results in Mastermind to the previous gold standard manual curation. And so just a top-line summary, in average, Veritas had identified about 8 relevant articles per variant, whereas Mastermind identified about 11 or 12 times more articles per variant, which is similar to what Birgit had highlighted. And I want to be careful here that this is not to suggest that Veritas is missing that many articles, because these are the 8 articles that they've highlighted are sufficient for the appropriate classification of the variant. But it is safe to say, as Birgit illuminated, that there were a very significant percentage of articles that were missed in the manual process just because of the sheer burden of information and the inability to devote many hours of human resource to look at all hundreds of those articles per variant. So again, to top line the results of this study, this is the correlation between the manual approach that Veritas had previously invoked using PubMed and Google Scholar versus the automated approach using the Mastermind software tool. And so overall, Mastermind identified 98.7% of all of the articles that we collected, all of those 3,600 articles, and identified 84% of the Veritas articles, with the union shown there in the purple in the intersection of those 2 circles. So this is meant to visualize, I don't think this is even close to being depicted at scale, but it's meant to emphasize that Mastermind has a high degree of sensitivity, and what we're trying to talk about in the next couple slides is enhancement of that specificity. I'll also emphasize here that the work that Birgit highlighted and the work that I'm showcasing is between a year and several months in the past. And as I suggested, because Mastermind has an automated technical platform, we are able to iterate and refine our algorithms and provide continual improvement to both the sensitivity and the specificity. One aspect of the improvements in sensitivity that I'll highlight is that we are beginning to aggregate and will soon launch supplemental data content into the Mastermind search engine results. And so it's likely that this 84% will become magnified once we have the supplemental materials included in our public-facing search results. So, pardon me, I'll top line this information because it's somewhat of a complicated graph to understand by saying that there's a strong correlation between the results of the manual article identification that Veritas very painstakingly collected, sometimes taking 2 to 3 hours per variant to identify these references, and the automated approach that Mastermind took of prioritizing the references that were most likely to be relevant and to make it on the final clinical report. And so that little box there is highlighting this plot, which indicates that overall, about 60% of the Veritas articles were ranked within the top 10 results for Mastermind. And situations where Mastermind had Veritas's articles below the top 10 usually indicated that Mastermind found equally relevant articles or more relevant articles that Veritas didn't need to find because they had identified articles that were already sufficient, or otherwise because for a given variant there were many hundreds or even 1,000 or more references that were identified, and Mastermind collected Veritas's results somewhere in the top 20 or 50 of those. And so that's all well and good. That's a high degree of correlation between the manual results that take a long time to accumulate, where all of the concerns that Birgit had suggested, are you missing something relevant, or this is taking far longer than we'd like to enhance automation in our workflows. All of that information there I'm summarizing, but let's reify it with a specific example so that I can more forcefully convey the benefit of using the Mastermind tool for variant curation. So this is a representative one of those 36 variants that we received and interrogated from Veritas. This is the UROS, or uroporphyrin 3 synthase gene. It's a missense variant, a cis to arginine missense variant at position 73. And I've chosen a missense variant because this typifies the pathogenic mechanism in the disease congenital erythropoietic porphyria. And two, it's more difficult to classify these missense variants using the ACMG AMP guidelines because you're not beginning with a PVS1, a pathogenic, very strong evidence, because this is not a known loss of function mutation. So Birgit highlighted in one of the earlier slides the lines of evidence that are useful for classifying according to ACMG and AMP guidelines. One is the population frequency, which I'm showing there from a representative data source, which is the exact population frequency. So it's a rare variant. It is the frequency is known and it's rare, and so that might qualify as some moderate evidence for pathogenicity for this disease, particularly where the mechanism of action is known to be frequently missense variants. There's also PP2, or supporting evidence by virtue of that very fact that missense mutations are a common form of pathogenicity, but I'll emphasize here that this is just a supporting line of evidence. It's not moderate or strong, and so it only contributes a modicum of evidence that this variant is pathogenic. And then the last line of evidence that I'll showcase here before jumping into the literature component is the computational studies, or the PP3 line of evidence, which is indicated by virtue of the fact that the cysteine to arginine change at this position was deemed by in silico models of pathogenicity prediction to, in fact, be pathogenic. But the point that I want to emphasize with this particular variant is those lines of evidence that Birgit suggested are pretty easy to come by are not sufficient, and are rarely sufficient in isolation to make the case that this variant is either likely pathogenic or pathogenic. In this situation, as in the mainstay of the variants that are curated, literature consultation and identification of empirical evidence from the medical literature is required to do diligence to the variant classification. In particular, 2 strong or 1 strong and 2 to 3 moderate additional lines of evidence are required. And so that's where the Veritas and others have previously relied on PubMed and Google Scholar, and increasingly labs, including Veritas, are utilizing Mastermind to make some of these determinations. So let's highlight some of those results for this particular variant. For PubMed, there's 7 results. PubMed, as you may know, only searches through the titles and abstracts of these references. And so in our own work, across many millions of references and many millions of variants that we've identified, that frequency of hits from a PubMed search for a particular variant is between 5 and 7.5%. So in other words, if you're reliant only on PubMed for this information and you're searching by variant, you're missing the vast majority of the references that are likely to be contributory to your pathogenicity determination. We contrast that here with Google Scholar results, which Birgit highlighted a bit of. In this particular case, there's 119 results. But some challenges associated with Google Scholar results, beyond what Birgit suggested of not being sure that you've identified everything, because Google Scholar has only some reach into the medical literature, it's crowded with duplicate references. There's a number of false positives that are occasioned in Google Scholar by a multiplicity of different mechanisms. And then I think, critically, it's not ordered. So particularly where you're, as a variant curator, you have 119 references, you don't know which ones to start with because Google Scholar doesn't put a clinical relevance calculation in their prioritization and data organization schema. So contrast that with the Mastermind search results, which in this particular case found 66 references, less than Google Scholar. But as I suggested, that's because there are no false positives for this search result in Mastermind, whereas there are a number of false leads and false variant matches in Google Scholar. Mastermind, in its proprietary indexing process, knows what those false positives are and eliminates them from the search results. And as I said, there's no duplicate information, so you won't see an abstract represented from 3 different websites and the full text mentioned as well, contributing to 3 or 4 search results. Mastermind consolidates those into a single reference point. And then, as I suggested, puts them in prioritized order, in this case, using the ACMG subcategories that are relevant to the Veritas method of interpreting the variants using ACMG and AMP classification guidelines. And just to again, put a specific face on some of these search results, when ACMG functional categories are invoked, one of the papers that is returned is this paper that I'm highlighting here, which is an exemplary paper that has a full clinical mouse model evincing the clinical features of porphyria for mice that are engineered to have this human URAS mutation. This was not part of Veritas's original search results for some of those reasons that we talked about earlier. And 2, in terms of the specificity of our search results, the Veritas articles that were identified for clinical reporting for this particular variant, every one of them appeared in the top 12 results for Mastermind, using the prioritization schema by invoking the functional category for ACMG. So again, Mastermind has a highly effective way of prioritizing the references that corroborates a lot of the manual work that had previously been done at Veritas and at other labs that Mastermind is utilized in, to minimize the time it takes to identify these references and confirm that they're relevant to the classification. And I think this is my last slide. I'll just emphasize that this is freely available. We'd like as many hands-on and eyeballs on the software as possible. We're a big proponent of the share the data movement, and so all of the data is available through the Mastermind free edition. If you sign up through the link that I'm providing there on the slide, you'll get 30 days of access to the professional features, which includes the ACMG classification criteria, as well as having unlimited searches and a handful of enhanced analytic components. But the core of the data is freely available to those who would benefit and would be inclined to sign up. So with that, I'll pass it back over to Christy, who I think is going to field our Q&A session. Happy to answer any questions that you have.
Thank you, Dr. Kiel. As a reminder to webinar participants, if you have a question, please type it into the Q&A box in the control panel. And before we begin the Q&A, we'd like to ask attendees to give us feedback by taking our exit survey after the webinar. And we'll now start the Q&A. Birgit, the first question is for you. Can the ClinGen and ClinVar and Decipher and Human Gen Mutation databases be considered publications or as strong as publications when it comes to evidence of variant interpretation?
Can you repeat? I didn't catch the first part. Can ClinVar and ClinGen be considered what?
Can they be considered publications or as strong as publications? Yeah.
Well, that's a good question. So, I mean, we all use them, these sources, and increasingly there's very useful information in there, especially of laboratories that share their evidence and have detailed evidence write-ups available. I've actually found myself referencing, a ClinVar assertion from a certain laboratory because the information was just nowhere else to find. But by and large, it's a double-edged sword, so I would be cautious. With one exception, there's an increasing number of expert panels in ClinVar, and so they're endorsed by the Clinical Genome Resource, or ClinGen. Those of you who do ClinVar searches frequently will know that those are labeled by 3-star status. So those, I think, those classifications have a much higher value, and should be able to replace much, if not all of your curation. I don't know if I answered the question.
Mark, do you want to weigh in on that as well?
No, I think Birgit got to the spirit of that question with the answer. I'll say that, well, Mastermind is, the database is predicated to date on all of the evidence from the medical literature. There's ways that we can use our indexing process to incorporate multiple different data streams, and we're very actively working on those, including working with ClinVar to include ClinVar data, working with Omen to incorporate some Omen-specific information, as well as incorporating some of those computational and population frequency data streams that I talked about earlier.
The next question is for both of you, and Mark, maybe you want to take this one first. I know you had a slide comparing some of the Mastermind searches to Google Scholar searches, but could you expand a little bit on how those two compare in terms of variant interpretation?
Yeah, sure. So permit me to get a little bit technical, but what I alluded to before is that Google Scholar is good at basic text matching, and Birgit suggested this too when she was talking about the sensitivity. It doesn't have an appreciation for the genetic code, the fact that cDNA and P dot nomenclatures can be overlapping, as well as the fact that a particular variant can have an RSID designation, which is definitely included in the Mastermind indexing process. And further, Google Scholar will frequently, in terms of false positive matches, will have a gene that's mentioned, say, in a supplemental table, and a variant that was searched for that's mentioned on the 50th page after the mention of that gene, and we'll link those two together. And so a technical aspect of refining the specificity of our search results in Mastermind involves identifying how close together those gene and variant mentions are in the text that is being searched, if they're adjacent to each other or if they're otherwise in the same sentence. That is definitely something that Mastermind utilizes in its indexing process, in addition to understanding contextually that this reference, this paper, this supplemental data is talking explicitly about and frequently about this particular gene. And so we've got studies that directly compare the Google Scholar search results with Mastermind search results. Those are in progress. Those are being written up now. But I hope I've given you a little bit of a taste of the differences in our approaches.
And Birgit, do you want to weigh in on your experience on that?
I would like to, yes. And I'd like to start with something that's slightly different from the question, but I end up with answering the question. So I want to just make sure that we all understand that the number of publications is what we are measuring right now, but it is not always a meaningful metric for labeling success or failure, in my opinion at least. So we have to keep in mind that the endpoint that the clinical laboratory wants to get to is the final classification. Now, what laboratories do not, or many laboratories do not do, is a full comprehensive curation of every single paper that's out there, which can get pretty daunting if you are in these looking at these well-established variants. So our mission is to stop when we are sure that we've exhausted the literature. And so Google Scholar is not our first choice, actually, at least not in my laboratory. We use it as a supplement. We start currently with, HGMD, which has, limitations. It is not complete, but it is sort of, I guess, a way to get to some of the most important papers out there, but not all of them. As Mark showed, we missed, a paper with an important mouse model, but we probably didn't go in this case further and do a full Google Scholar or PubMed search because we already arrived at a pathogenic classification. So that's, I'm not saying that this is the approach that everybody's taking, nor it may not be the right approach, but that's sort of our approach. Google Scholar is clunky and messy and, has too many limitations to use it as a primary search tool, in my opinion.
I'll jump in and echo that I totally agree with Birgit. And in fact, what you'd like to do is have the minimum number of references that are sufficient to make the call. And so that's what I'm hoping I had come across in my portion of the talk.
Okay, great. Thank you both. Mark, did you mention that the Mastermind is going to be integrated with Omen? We had a question about that as well.
No. So Omen's data is licensable for inclusion in third-party software packages, and there's the likelihood that we will be incorporating some of that data into Mastermind. It's a separate question whether Omen will host Mastermind links. So to short-line that, it's not necessarily a reciprocal interaction. We do, however, have reciprocal agreements with some third-party data providers that are featured in some of the Mastermind links, and two are featured on those different database websites. Omen is not one that we've discussed integration with, although, as I say, we're internally considering bringing Omen's data and licensing that for display in Mastermind.
Okay, great. Thank you.
Yep.
The next question is again for both of you. One of the most important needs for a clinical lab is the confidence that a null search really means that there are no publications. So could you speak to a little bit more about the degree of confidence that you have when no publications are identified in Mastermind? Birgit, maybe you could field that one first.
Sure.
Well, actually, I find that one difficult to answer because I didn't know. I actually don't have a good answer for that. Mark, you would probably better.
Sure. It's a challenging question to answer. It's one that we frequently get from late stage adopters. The way that we choose to answer it typically is no search engine will ever have 100% of the results. And what we like to highlight is rather than the fact that in every circumstance we have found every article that ever mentions this particular variant, we like to say and highlight the fact that we are much more comprehensive than any other tool available. So Birgit alluded to one of those vendors, HGMD, and I think the QCI platform. We've had anecdotes from some of our customers who indicate that there are many papers that Mastermind has identified that are not found in those references. And so without giving you a specific number that indicates that we have every article for every one of these millions of variants, it's, I think, fair to say that we have the most comprehensive database of literature available.
And let me jump in now because now I thought a little bit about that question. The data that we have, I think, doesn't allow to answer the question 100%, but what it does allow me to say is that Mastermind and the way we used it didn't miss many papers that PubMed found. If a Mastermind null search now without doing this bake-off returns nothing, that doesn't mean necessarily there are no papers. It means that there are likely also no papers in PubMed. But PubMed can also be, annotated incompletely. So I find that's why I found it difficult to answer. I hope that makes sense.
I think, yes. Birgit, you said it quite rightly. A bake-off is what's required. And I'm trying to set expectations appropriately to say that no search engine will ever find every. And so what you're looking for, as Birgit and I have been highlighting in the talk and in these answers, is sufficiency. and utilizing the best, most efficient resources to strengthen your confidence in reporting a null result.
Great, thank you. Birgit, can you speak to the cost in money, time, other resources associated with obtaining articles for variant curation? And in your experience, does Mastermind increase or decrease those costs?
Yeah, that is the key question. Absolutely, I can comment on that. Now, I will say conventional search strategies that do not include Google or PubMed, which are free, are prohibitive depending on the environment you operate in. So as you probably all know, there are, hefty licensing fees for databases that, we have to access, or we like to access, let's put it this way. So if you're operating in an environment that is, charged a lot of money for accessing data, then Mastermind, I believe, would result in a significant reduction. It all depends on how you're set up in your institution. It is probably not, necessary for everybody, but, I would say it cost-wise, but, if the accuracy of the searches should be another convincing argument.
Okay, great. Mark, does Mastermind use language modeling techniques to search the context as well as looking for a search term? For example, a paper could just refer to a variant as an alternative hypothesis rather than the main finding of the paper. So would Mastermind make that obvious to whoever is searching for a search term?
Yeah, so we would make it obvious in the way that we present the sentence context for those mentions, and then also, too, it would be apparent in the relative prioritization of those references that we've put up in the search results. And so there's a variety of context cues, not least of which is the clinically relevant key terms and their frequency and propinquity to the variant mention, things like identifying consanguinity or the keyword suggesting consanguinity and the presence of a particular variant, or otherwise the presence of two variants in the same sentence. And so that's a flavor of some of the natural language processing activities that we use to drive the prioritization. But again, our modus operandi is to show all of that evidence so that our word is not taken on face value, but rather that information is readily interrogable by the user.
And do you have any plans to take further steps to automate ACMG or AMP guideline-based classification based on literature data, such as providing preliminary variant classifications for curators to review?
Yes, we definitely do. We've got a couple of lines in that water, not least of which is working with Birgit to, as I said, continually to evolve and improve the specificity of the search results. I want to emphasize here that we don't expect to put anybody out of work. There's enough work to go around, and there's too few individuals who are trained and expert enough to do the variant interpretation. Our approach here with building the software is meant to facilitate the efficiency of that curation work. And so along those lines, we're hoping to build more automated ACMG classification features and specifications in the Mastermind software, but never will we have the intention of having that be just trusted de facto. It will always, I think, require a manual review. What we hope to do with Mastermind and some of these enhanced features is just make that manual review much more efficient, much more accurate, and far less painful.
Mark, would you consider making a track available on the UCSC genome browser as to whether Genomenon has identified literature about a gene or a variant within a gene?
I don't think that was a planted question. That's perfectly timely because we've actually just been in conversation with some of the data scientists at UCSC to have just that, a data track of all of the variant information, all of the numbers of citations for each of those individual variants in the UCSC browser itself. I think we're going to know in a matter of months here when that's going to go live, and we'll be sure to let attendees know.
Great, thank you very much, and I'm afraid that's all the time we have for today. We'd like to thank Birgit Funke, Mark Kiel, and our sponsor, Genomics. If we didn't have time to get to your question, we will try to follow up with our experts. As a reminder, please look out for the pop-up survey after you log out to provide your feedback. If you missed any part of this webinar or wish to listen to it again, a link to an archived version will be emailed to all attendees. Thank you for joining us for this Genome webinar.